everyone. Thank you for watching this video. I am Shebnem and I'm delighted to join CSAT this year. I'll go through my poster, hoping to chat with you soon and discuss cold spraying. In this research project, we studied the cold spraying of polystyrene particles on various plastic and aluminum substrates with a high pressure cold spray setup. We used the VRC setup built in School of Mines campus, which is mainly used for metallic and ceramic cold spraying applications. Figure 1 shows a basic schematic of the cold spray setup with the nitrogen gas, powder feeder, heating element, nozzle, and the substrate. Although this figure shows the substrate vertically, our substrate was oriented horizontally and the nozzle perpendicular to the substrate. We changed the gas temperature between 60 to 120 C to stick around the glass transition temperature of polystyrene, which is around 95 degrees Celsius. We kept the gas pressure and the lower spectrum between 250 and 500 psi, knowing that the polymer particles would prefer lower speeds when compared to metal particles. And this is our design of experiment table. The middle column in this poster shows the results for plastic substrates. We tried 3 different plastic substrates: polypropylene, polycarbonate, and a mixture of polycarbonate and ABS. Figure 2 shows the deposition thickness of polystyrene with only 2 passes with varying gas temperature and pressure. The top graph is at 250 psi in varying gas temperature, and the middle one is 400 psi, and the third one is 500 psi. We wanted to determine the best temperature for most substrates, so we went with 100 degrees C. Since we only did 2 passes with the plastic substrates, we wanted to make sure we're actually depositing polystyrene powder on the surfaces. Therefore, we ran an FTIR analysis on the surfaces. The figure 3 shows the results of FTIR. The top graph shows the polypropylene surface as it is with no carbon hydrogen stretching. The second graph shows the coated polypropylene surface with carbon hydrogen stretching peaks appearing. And the third graph is an FTIR graph of the pure polystyrene powder for comparison. You can see the carbon hydrogen peaks here. Now that we were sure that we coated polystyrene on the surface and picked the gas temperature, we wanted to observe the effect of substrate heating. For this, we conducted 2 sets of experiments with 10 passes with and without substrate heating. Figure 4 shows the deposition thickness of polystyrene at different gas pressures at 100-degree gas temperature. As you can see, the deposition thickness increases with the gas pressure when the substrate heating is on. So for the plastic substrates, we concluded that when we kept both the gas pressure and the substrate heating around the glass transition temperature of polystyrene, we successfully coated them. With the aluminum substrates, we used 60-60 composition with 3 different surface roughnesses. We prepared different surfaces with milling, sandblasting, and Scotch-Brite treatment. Then we conducted the same first set of experiments to determine the optimum temperature. For the milled samples, the deposition thickness was the highest when the gas temperature was at the lowest end, 60 degrees C, increasing with increasing pressure. However, for the other substrates, the deposition thickness decreased as the gas pressure increased, indicating weak particle adhesion in the first layer. Still, we cannot conclude, but we should investigate the bonding mechanism of the particles to come to a conclusion. For future work, since the polymer particles successfully deposit on different substrates when the particle temperature high and velocity is low, we decided to use a powder heater. This would let the particles heat up, but keep the gas temperature on the low end to keep the velocity low. Another approach we tried, and we will investigate more in depth for the aluminum substrates, is to decorate the polystyrene particles with aluminum particles to help them build a more substantial first layer. Figure 7 shows an image of the aluminum substrate with only 2 passes of coating decorated of polystyrene particles. In conclusion, we decided that we made a good progress on the plastic substrates and that we need to investigate the first layer adhesion on aluminum substrates more. We would like to thank Forrest Thompson, Whitney Duffy, and Dr. Kat Donovan for helping us throughout this project. Thank you for listening.